All right. So last time we talked about graphing parametric functions. We talked about how to go from parametric to Cartesian form. And we talked about how to go from Cartesian form to parametric. Can you please stop talking? Today I want to start by doing one more example of going from Cartesian to parametric, and then we'll start in on new things for today. Okay? So we're going to do a little bit more here. Not right now, Andrew. Okay, so let's say we want to define the parameterization of a line segment through -1, 4 and 6, 3, or 6, -3, excuse me. So the idea here is that I'm going to write a vector equation for the line and use that to create my parametric function, just like we did yesterday. So the vector equation for a line is r equals r0 plus vt. Remember, r0 is a point vector, so I can use either one of my points. So for the sake of this problem, I'm going to use the first point, but it doesn't really matter. And the vector v is our slope vector or direction vector. So I'm going to use the vector cd. So that's going to be 6 minus -1, and then 3, or -3 minus 4. Everybody's okay there? So this vector equation immediately gives me my parametric function, where the x components of my vector equation is my x parametric equation, and the y components of my vector equation give me the y parametric equation. The only thing that I still need now is my interval for my parameter. Since this is a line segment, that interval is not going to be infinite long, right? So let's think a little bit about what's going on here. Notice that one of the endpoints for my segment is also this point in my vector equation. So what value of t do I know I need to have in this interval? -4? -1 and 4. No. So look at our vector equation. 0. Right? So if t equals 0, that last vector is going to drop off, and you're going to be left with the point -1, 4. Everybody see that? All we need to do now to figure out is determine which way our slope vector is pointing. Is it pointing like to the right or is it pointing to the left? The easiest way to do this is to just kind of, stop talking please, is to check using these two values of t. So if t equals 1, I'm going to get -1, 4 plus 7, -7, which gives me the vector 6, -3. Is that what I want?
No.
It's not?
Yeah.
It is, right? Great. So that's what I need. So what's my interval of t going to be? 0 to 1. The advantage of using a vector equation to kind of create my parametric function is that my parameter interval for a segment is always going to be like a unit interval. It'll always be 1 unit long, whether it's going from -1 to 0 or 0 to 1. It'll be one of those two. So that's nice because it's kind of always the same. All right. On to our next topic. So in the next section, we're going to look at some applications of parametric functions. Specifically, one of those is going to be projectile motion. Quick show of hands, those of you that are currently in a physics class or have taken a physics class. So there's
I actually just took a test.
a handful of us. So those of you that have been in a physics class, this will probably look a little bit familiar. Okay. So the height s in feet and the vertical velocity v in feet per second of an object in free fall, ignoring friction after t seconds, are given by the functions s of t is equal to 1/2 gt squared plus v naught t plus s naught, and v of t is equal to gt plus v naught. So let's just identify what some of these other letters are here. So what does G represent? Gravity. What is the value for gravity? Okay, -9.8. But remember the unit. What is the unit on that? Meters per second. What unit are we working in? Feet. Does anybody remember gravity in feet? It's -32. So if we do that, this becomes -16t squared plus v naught t plus s naught. And then we have -32t plus v naught. what does t represent? Time in what unit? Seconds. What does v naught represent? Close. Initial velocity. Thank you, physics students. And what does s naught represent? That's the initial height. The initial height. If you want to, but I'm writing s's.
So S is the initial height?
Well, yes. Again, no. S naught is the initial height. The height is just s. So the height at time t is s of t. Okay. Just as a side note, why is gravity negative?
Because it goes up.
Good. It acts down. All right. So let's do an example.
What is after above the water? What I just flared, like a strong flare?
Yeah. That's correct. Okay. So here we say that a ship is stranded at sea on top of the bridge, 80 feet above the water. Distress flare shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height against time and find the height of the flare at times 1, 2, 4, and 5 seconds. Huh? How about the? That's okay. So what quantity are we interested in here? The height of the flare, right? So which equation am I going to use? That, yeah, S of t. Okay. So can you guys stop, please? Okay. What are we filling in for V of t? 72. And what are we filling in for S naught? 80. Okay. So we can just go ahead and do this on our calculator then. I'm going to turn this back into function mode because there's no reason I should graph this using a parametric since there's only two variables involved here. So x is time. I'm just going to guess at, say, 10 or something. And y is the height. I don't know, I'm going to just guess at like 200 or something. And there's a picture of my flare. So remember, the x-axis is time and the y-axis is height, because this flare is just going straight up and down, right? So if I want the height at time 1, the easiest way to do this is to press second, trace, and choose the value command, and pick x to be 1. In that case, it tells me the y is 136. And I'm just going to repeat that 3 more times for t equals 2, the height being 160, for t equals 4. Oops. The height is 112, and for t equals 5, my goodness gracious, the height is 40. Is everybody okay with that idea? I just showed you how I got those values. I used the value command. I just told you how to do it. You were talking to Isabel, though.
That's true.
That's why you missed it. Okay, you kind of saw it, but you still weren't listening.
It's okay.
What if we wanted to like physically model what this flare was doing? Right? The graph that we were just looking at isn't like an XY graph of the flare's position. The flare's not making like an arc like this. It's just going straight up and coming straight down, right? Everybody agree with that? To do that, to actually describe or graph the flare's motion, we can use a parametric function to do this. In this case, how much forward or backwards, left and right, is the flare moving? If you're just shooting it straight up and down. 0. Good. And the flare's vertical motion can be described using the equation that we just graphed a moment ago. Get those out there. Okay. That seems, I should probably do that. That seems fine. Okay, why can't I see it? Nope. Where is the x coordinate at that we picked? 0. So where is it on the graph? It's hiding under the axis. So just so we can see it, instead of using 0 here, let's use 1. There it is. Everybody okay there? Shocking, it's just a straight vertical line, because really that's what the flare did. We shot it straight up and then came straight back down. Everybody okay with that idea? Now, this, to deal with that kind of a situation using a parametric equation is kind of overkill, right? Where the parametric function really becomes more valuable to us is if we do something at an angle. Like if you're throwing a baseball or shooting a cannonball or doing something where things are moving both up and down and left and right. those are situations where we can describe that motion using a parametric function quite nicely. We call that situation projectile motion. Okay. An object in projectile motion with initial angle theta taken from the horizontal and initial velocity magnitude of v in feet per second can be represented by the vector v equals the magnitude of v times cosine theta, comma, the magnitude of v times sine theta. The distance and height in feet are given by the parametric function x equals the magnitude of v times cosine theta times t, and y equals negative 16t squared plus the magnitude of v times sine theta times t plus s naught. The horizontal velocity v sub x and vertical velocity v sub y in meter or feet per second are given by the function parametric function v sub x equals magnitude of v times cosine theta, and v sub y equal negative 32t plus the magnitude of v times sine theta. So we can use these new equations to deal with some more classical projectile motion that are not just straight up and down. Okay. We hit a baseball at 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence? If so, oops. Yep. That 15-foot fence is 300 feet away. If so, how much does it clear the fence by? If it doesn't, where does it hit the fence? Like how high up the fence does it hit it? So looking at these last two set of parametric functions, which ones do we want? The x and y or the vx, vy? X and y, very good. Y. What is x representing? The horizontal distance. Are we given, do we know something about the horizontal distance? Yes. What does y represent? The vertical distance. Do we know something about the heights? Yes. That seems like the logical choice then. Okay, so what is my value for the magnitude of V? What does the magnitude of V represent, actually? Let's start there. What did we say that was? Raul?
135.
Okay, it's the initial velocity, which in this case is 135. Good. And then what's theta? 16. Okay. And what is S naught in this case? 3. That's the initial height of the ball. Everybody okay here? Okay. So, what is going to be my plan? Bye, Gabe. What I'm going to do is I'm going to take 300 feet and plug that in to x to figure out how long it takes the ball to go 300 feet. Once I have that, I can use that time and plug it into t in my y equation to figure out how high off the ground the ball is when it's 300 feet away. Yes. Is everybody okay with that idea? So when I type that all into my calculator, I get about 3.51 feet. So what would how would I answer this question? Is the ball going to clear the fence?
No.
No. Why not?
The fence is 16.
Yeah, it's 50. Since that's less than 15, the ball does not clear the fence. It hits the fence 3.51 feet above the ground. Everybody okay with that idea? All right, let's graph this to get a picture of what's going on to reinforce what we're seeing here visually. So I want to make sure my calculator is in degree mode and parametric mode. So that's the first thing I'm going to do. And then I'm going to go to my y equals menu. And for my x equation, I want to type in 135 cosine 16 times t. And for my y equation, I want negative 16 t squared plus 135 sine 16 times t plus 3. Oops, I think I missed the plus sign there. Yeah, plus 3. Okay. Everybody's okay with that? That's going to describe the path of the ball. What I'm going to do now is I'm also going to draw in the fence. What x coordinate is the fence located at? How far away is the fence?
300.
So 300 is what I'm going to put in for my value for x. And how tall is the fence supposed to be? 15. So what I'm going to do here is I'm going to do 15 divided by the variable t max. What t max is just the maximum t in my interval. So to get the t max variable, I'm going to press the vars button. I'm going to go to the Windows option and then over to the t theta tab. And there's the t max. And then I'm going to do times t at the end. Vars, Windows, over to the t slash theta. Yep. Okay. So the last thing I need to do is set up my window then. So those of you that are baseball players, how long does it take? How long does a ball that's hit like 300 feet stay in the air? Just give me a rough estimate. 5 seconds seems reasonable. Okay. The values for x, well, we're going 0 to 300, so I want a little bit more than 300. I'll pick, say, 400. Sound good? The y, how high up in the air do you think this baseball is going to go? Just guesstimate. 200 feet up? I think you guys are crazy. I'm picking 50.
The X max was 400.
That's what I picked. Why am I picking such a low height? Well, 300 feet's pretty far to go. It's the angle that the ball was hit at. 16 degrees is not very high, right? Like, that's like a line drive. That's not going very high up. So there's my baseball's trajectory. There's my fence. So we're hitting the fence, right? It's assuming that the outfielder's not standing in front of the fence. All right. Let's do another. Sound good? Okay. Jeff hits a baseball 3.5 feet above the ground with an initial speed of 141 feet per second at an angle of 24 degrees. Will the ball clear a 20-foot fence 400 feet away? If so, by how much? And if not, where will it hit the fence? So, let's set this up almost exactly the same way as the previous problem. So what am I going to write for my x equation? X equals what? Who can tell me? (141 cosine 24 t). Good. And how about our y equation? Okay. Negative 16t squared plus 141 sine t plus 3.5. I think you might have said cosine. Everybody's happy there. Okay. Since we have everything all set up in our calculator, let's just change our parameters here and get a quick visual and see what's going to happen. Sound good to you guys? So I'm just changing my 135s to 141s. I'm changing my 16s to 24s. Oops. And my 3 to 3.5. My 300 changes to 400, and my 15 changes to 20. Everybody's good with that? Okay. We'll change our window now to reflect this. So time of baseball is going to be in the air for 400 feet. It's probably still 5 seconds is a decent estimate. Since our fence is at 400 feet, I'm going to make my X max now 500. And because my angle is a little bit, we're going a little bit more up at a 24 degree angle than a 16 degree angle, I'm going to change that Y max to maybe be 100 this time. And then I'm going to hit graph. So there's my ball. There's my fence. What happened? It didn't clear it?
No, it didn't.
It did, right? So let's see by how much. Sound good? So we'll do this the same way. So I'll use my x equation to solve for t, and then I will plug in that answer in for t into my y equation to figure out that height. When I do that, I get about 27.3 feet. Since this is bigger than 20 feet, say the ball clears the fence by 7.3 feet. Is everybody okay there? Okay? What if we operate under the same situation and say, like, assuming there's no obstructions, how far will the ball travel before it hits the ground? So in this situation, what are we looking for, x or y? X. Great. So we're going to use the y equation to solve for t, and then plug that answer in for x. Okay, so what is going to be the value for y when the ball hits the ground? 0. Okay. So I'm just going to say 0 equals negative 16t squared plus 141 sine 24t plus 3.5. How would I solve something like this? What kind of an equation is this? Quadratic. How would I solve this then? So using the quadratic equation is what I would do. So I would say t is equal to negative 141 sine 24 plus or minus square root of 141 sine 24 squared minus 4 times negative 16 times 3.5 all over 2 times negative 16. So when I type that into my calculator, I would get these two answers. Do both of these answers make sense? No. Which one doesn't make sense? The negative. Time's not negative. So this is the answer that we need. What are we going to do with this answer? I'm going to take my x equation and plug in that value of t. So that ball is going to travel about 469 feet before it hits the ground. Sure. Jeff just crushed it. Okay. One more question. So our last question is, what is the furthest away from that starting position you could place that 20-foot high fence and still have the ball clear the fence? Stop talking, please. So which are we looking for, x or y? X, right? Because we're asking farthest away. That's the x. So we're going to use that y equation to solve for t, and then plug that into our x equation. What value are we going to put in for y here? What was that? How high the fence is. So 20, right? Which is how high the fence is, right? Yes, exactly right. Okay? So, yes, sir. Yep. This is a quadratic. To solve a quadratic, it must equal 0. Okay? This, just like we did before, we'll use the quadratic formula. So this gives me two solutions. Now, at first glance, both of these seem feasible, right? Because both the times are positive. Which one of these is the one that I want? The bigger one. Okay, why am I getting two answers here? What is this value of t representing? The time when what? The time when the ball is 20 feet above the ground. So you have one time right as soon as you hit it on the way up, and then you have another time on the way back down, right? That's why you're getting two answers here. If you want to place the fence as far away as possible, you want when the ball's on the way back down, right? That's much further away than when it's on the way up. You guys agree with that? Okay. So this is the answer that I want. So I'm just going to plug that into my equation for x. And what I get is about 421.07 feet. What do you guys think? It shouldn't be too bad, right?